Okay, so the question number one, let G be a group of order 39, order of H is 3 and order of K is 13, unique subgroup of G, then which of the following statements is true? So I'm going to use a theorem. Okay, let G be a finite group having two normal subgroup H and K such that G equal to HK and H intersection K is identity, then G is isomorphic to H cross K. So here order of G is 39. 39 equals to 3 into 13. So order of H equals to 3. H equals to Shiloh 3 subgroup and order of K equal to 13, where K equals to Shiloh 13 subgroup. We know that any Shiloh subgroup is normal if and only if it is unique. Hence here H and K both are normal. Again, order of H intersection K is 1 because H intersection K is subgroup of both H and K. So order of H intersection K must divide order of H as well as order of K. Since order of H is 3 and order of K is 13, so they are co-prime. Hence order of H intersection K is 1, which implies that H intersection K is trivial. Hence we can use the above theorem which I have already stated. Hence G is isomorphic to H cross K. Now H is a group of order 3, that means H is isomorphic to Z3, and K is a group of order 13, hence K is isomorphic to Z13, because we know that any group of order P where P is prime is always cyclic, and Z3 cross Z13 is isomorphic to Z39 since 3 and 13 are co-prime, which implies that G is a cyclic. Okay, the next one is, we know UMN is isomorphic to UM cross UN if GCD of Mn equal to 1, where UN is basically the group under multiplication modulo n. Okay, so UMN is isomorphic to UM cross UN if GCD of Mn equal to 1, and U2 power n is isomorphic to Z2 cross Z2 power n minus 2. I'm going to use these two results. This is pretty trivial results, and by using this we can easily solve this problem. So option A, U5 is isomorphic to Z4 and U8 is isomorphic to Z2 cross Z2. Hence this option is wrong. Option B, U10 is isomorphic to U2 cross U5 by above property, which is isomorphic to trivial group cross Z4, which is basically Z4. But U12 is isomorphic to U3 cross U4, which is isomorphic to Z2 cross Z2. So this is also wrong. Option C, U8 which is isomorphic to Z2 cross Z2 and U10 which is isomorphic to Z4. This is also wrong. So option D, U8 is isomorphic to Z2 cross Z2 and U12 is isomorphic to U3 cross U4. which is isomorphic to Z2 cross Z2. Hence option D is correct. Okay, the next problem. So we know order of an element in Sn is basically determined by LCM of length of cycles in disjoint cycles representation. That means we can write each element of Sn as a product of disjoint cycle, and if we take the LCM of the length of that cycle, we will have the order of that element. Okay, so as a result, in S13 I can take 6 cycle, 7 cycle, I have order 42. I can take 5 cycle, 7 cycle, I have order 35. I can take 3 cycle, 4 cycle, 5 cycle, I have order 60. And you can see there doesn't exist any element of order 27, because you can't occur 27 cannot be occurred as a product of cycle where each cycle has length less equal to 13. Okay, it is not possible that LCM can become 27. Hence option A is correct. Okay, the next problem is that this is a very nice problem. That given that G be a finite group such that there exists X not equal to identity in G where X is conjugate to X inverse. I am using this notation for telling that it is the X and X inverse are conjugate. Okay, then what can it be? So take S3. Okay, 1 2 3 is conjugate to 1 3 2, because we know that in Sn any two permutation is conjugate if and only if they have same cycle representation. But S3 is non-abelian as well as non-cyclic plus non-abelian, hence CD false. So basically whatever example you can take, it is obvious that you should take some easy example, because most of the cases the counter occurs from the known example and the group of small order. Okay, so S3 is the first non-abelian group we are going to introduce because it's the smallest order non-abelian group. So you can easily discard C at D option, but the thing is that it is quite important to understand why the option A is correct. Okay, so proof of option A, because option B says that it is not necessarily even, so that means you need to prove option A. Okay, so if possible order of G is odd. Okay, and there exists X not equal to identity such that X is conjugate to X inverse. If X equal to X inverse, then X square equal to identity, then 2 divides order of G. That is a contradiction, because I am assuming that order of G is odd. Now let X not equal to X inverse and X and X inverse are conjugate. We know that conjugacy class, order of the conjugacy class is same as order of G by order of the centralizer of X. That means order of the conjugacy class that divides order of G. Now since order of G is even, that will imply that order of conjugacy class, order of G is odd. I am assuming that order of G is odd. Hence order of the conjugacy class of X is also odd. Right? Now X inverse belongs to conjugacy class of X. Since conjugacy class of X has odd order, that means there exists Y not equal to identity such that Y belongs to conjugacy class of X. That means Y is conjugate to X. That means Y is G inverse, right? That means Y inverse is X inverse G inverse, right? Then Y inverse is conjugate to X inverse. So in particular, Y is conjugate to X is conjugate to X inverse to Y inverse. That means X inverse, Y inverse all belongs to conjugacy class of X, right? So if you choose any non-identity element in the conjugacy class of X, you will always find that that element's inverse is also belong to that conjugacy class of X, right? And so we know that identity element cannot be conjugate to any non-identity element. So conjugacy class of X cannot have identity element. So if any non-identity element is there, that means their inverse is also there, right? And also since order of G is odd, so it cannot have any element of order 2. So X and X inverse is always not equal there, right? Any non-identity element for any non-identity element X not equal to X inverse, which implies that conjugacy class, order of the conjugacy class is even, which is contradiction to our assumption. Okay, hence order of G cannot be even. Order of G is always, sorry, hence order of G cannot be odd. Order of G is always even, hence A is correct. Okay, so next come to the next question, that which of the following groups has an element of order 1 2 3 4 5 but doesn't have element of order 6. First of all, S5 and S6 you can directly discard it, but because S6 has an element 1 2 3 4 5 6 which is order 6, and S5 has an element 1 2 3 4 5, that is LCM of 2 and 3 which is 6. So both have order 6, so C and D is discarded, right? Wrong. Option A is correct, because in A5 you have this trivial element order 1, order 2, order 3, you have order 4, you have order 5, but you cannot have any element of order 6. You can easily check, because the same thing is happened, but you need to find out even elements of even permutations in this case. So sorry, this is A6, but in A5 you cannot have any element of order 4, because there you have not this the symbol 6. So you need to do anything whatever you can do by just choosing the element from 1 2 3 4 5, but you can easily see that there doesn't exist an element of order 4. Okay, hence A6 is correct answer. A6 is correct. Okay, okay. Question number 12. Question number 12 is pretty difficult to actually solve, but you can do it by intuition. That it says that center of orthogonal matrices, center of orthogonal matrices is basically identity and minus identity. Yeah. Hence the answer is 2. It is difficult to prove exactly. When we prove is lengthy, you need to it's not so trivial if you don't know. Okay, so I'll skip that proof because it takes some time to give you detailed argument. But it's a result based question. Like if you know, you can solve it. Okay, but intuitively you can see that this is going to happen. Okay, right. Now what is the question? Now I am going to solve a problem. Try to check that is there any other problem is there. Okay, so let me check it again. Yeah, so there is another problem. So problem number 33, that is an MSQ sections problem. I think same type of question comes in the last year in 2023 also, and you should know this properly, right? So additive group of real numbers, is it isomorphic to additive group of rational number? That is clearly false, because R is uncountable, but Q is countable. So they are not the set as a set level, they are not even bijective. Hence, it cannot be possible to be that they are isomorphic as a group. Okay. So the next option is that additive group of real numbers is isomorphic to multiplicative group of non-zero real numbers. So additive group of real numbers and multiplicative group of non-zero complex numbers. Sorry, multiplicative group of non-zero complex number. So you can take -1 here. So -1 square equal to 1. That means -1 has order 2. -1 has order 2. But there doesn't exist any element of order 2. Because if that is true, then 2x equal to 0. That means x equal to 0, which is not possible. That means they are not isomorphic. Okay. The option third says that multiplicative group of non-zero real numbers isomorphic to multiplicative group of non-zero complex number. Means R star with respect to dot isomorphic to C star with respect to dot. You can take I that is imaginary, square root of -1. It is I. I has order 4. There doesn't exist any element of order 4. Okay. That means they cannot be isomorphic. But option A is true, that R plus is isomorphic to non-zero positive real numbers. And in particular, you can explicitly give the map the isomorphism x goes to e power x. Okay. So e to the power x is basically onto, right? Because x is onto here. So this is a surjective map, and you can see that this is the group homomorphism because e power x plus y is same as e power x dot e power y. And also you can see that kernel is trivial because e power x is 1, that will imply that x equals to 0, right? Hence this is the isomorphism. X goes to e power x, this is the isomorphism. Hence they are isomorphic. Okay. Hence they are isomorphic. That is true. Okay. Now come to the question number 36. Option A. If G is non-abelian, right? Then G clearly not equal to ZZ. That means Z mod ZZ is greater or equal to at least 2. I mean Z mod ZZ is non-trivial, right? Hence A is false. It is obvious. For D, take order of G is 2 cube, which is 8. Take Q8, D8, dihedral group, right? These are non-abelian, right? And here we consider P equal to 2, so that's the counter example. So option D is also false. Okay. What about proof of option B? Option B, C are correct, but I'm going to prove it. So order of G is greater or equal to 2, means there exists a P such that prime P such that P divides order of G. By Cauchy's theorem, G has an element of order P, right? Say, now I'm going to define a map phi from Z to Z. Phi of 1 is A. That means phi of n is A power n. This is clearly a group homomorphism. Okay. And kernel phi is basically PZ. So phi is non-trivial group homomorphism. Group homomorphism. Hence option B is also correct. Now come to the option C. G is non-abelian, right? That will imply ZC not equal to Z. That will imply G mod ZC has order at least 2. Now we know G mod ZZ is isomorphic to in Z. Inner automorphism of group G. Inner automorphism of group G. Okay. Hence, order of inner automorphism of group G is at least greater or equal to 2. That means we have a non-trivial homomorphism, non-identity isomorphism from G to G. because it is greater equal to, order is greater equal to 2, and any in G is basically an automorphism, inner automorphism. Hence this is correct. Okay, hence this one is correct. So these are the all group theory questions that comes in uh, that came in IT Jam 2024. I'm going to solve the other problems also. I'll try to solve, at least I'll try to cover the all pure mathematics questions, because okay, because applied mathematics questions is very lengthy to solve, and also we have need to draw more diagram to understand the problems related to integral calculus and so on. So I'll try to at least explain the questions of pure mathematics questions. Okay, I'll try to make other videos for topic wise. Okay, so this is the first video. Thank you.